all to this wonderful talk today. This is the 5th talk in the series of our online monthly talks. Let me start by introducing Indian women in mathematics a little bit. It's a collection of mathematicians that has been in existence since 2009. Our objective over the years has been to encourage more women to pursue higher education in mathematics and to organize events and networking opportunities that will enable them to take up career in mathematics. Our main sponsors who give us grants to run these activities are National Board of Higher Mathematics and DA Government of India and Committee for Women in Mathematics, International Mathematical Union. They support our activities since 2016. Current activities can be seen on our website. I hope all of you know our website. It's also there on our poster. We, in recent years, have been running 2 regional workshops and an annual conference every year, and also a visitors program where we invite distinguished women mathematicians to go and to remote places in India and give a talk and have interaction with women, especially women students and faculty from that remote region. Last year we have also introduced a workshop for young women who are studying in an undergraduate program. This is 1-week workshop we started last December, and this year we have a follow-up workshop which is starting soon. This visitors program also we had women mathematicians going to remote places and giving talks. This year, due to pandemic, we cannot have any activities in physical form. So we decided to have this series of online talks. This is the 5th talk by Professor Malabika Pramanik. So let me introduce Malabika Pramanik. Today's talk is titled On Sets and Patterns. Professor Malabika Pramanik will be with us very soon. Let me say a few words about her. She is an outstanding mathematician. Professor Malabika Pramanik is a professor of mathematics at the University of British Columbia. She received her bachelor's degree and master's degree both in statistics from Indian Statistical Institute, Kolkata. She obtained her PhD in mathematics from University of California at Berkeley in 2001. Before joining UBC in 2016, Professor Pramanik held positions at University of Wisconsin, University of Rochester, and California Institute of Technology. Professor Pramanik's research interests cover vast areas of mathematical analysis, such as Euclidean harmonic analysis, partial differential equations, and several complex variables. She is widely recognized as one of the most talented analysts of her generation. She is the recipient of several awards for both her research and her teaching. Among these awards are UBC Killam Teaching Award, the Ruth E. Mishler Memorial Prize, and the prestigious Canadian Mathematical Society Krieger-Nielsen Prize for Research Excellence. Professor Pramanik is actively involved in initiatives that promote diversity and inclusivity in STEM fields, especially through her role as Vice President for the Pacific region of the CMS and as a co-organizer of programs such as the PIM's Diversity in Mathematics Summer School. She has been the director of Banff International Research Station, BIRS, since July 2020. Before we start with the talk, let me inform you all that Professor Pramanik will join us very soon. You can put your questions on the chat, and they will be taken up at appropriate uh, time. Uh, let's start with her talk on sets and patterns. Thank you.
Hello, everyone. First off, I'd like to thank Professor Nikita Agarwal and the Indian Women and Mathematics Visitor Program Committee for the invitation to speak here today. I have long admired the work that IWM does in terms of providing great opportunities for women mathematicians of all career stages in India. I am deeply honored to be able to participate in their activities in a small way. My talk today is on sets and patterns. Without getting into heavy technical machinery, I want to give you a flavor of a genre of problems that has fascinated me for years. Some of these problems are deceptively simple in their formulation and notoriously difficult in their resolution. Some others have launched many fruitful research directions. My hope is to share some of these questions and point to some significant advances in this area. I will stop for a question answer session after that. Nikita mentioned the possibility of a discussion of career prospects. For this part, I will let the audience guide me on what would be most relevant for them. Here is a rough outline of my talk. I will start with a general idea of what I mean by a pattern problem and follow it up with some representative examples and key definitions that play a fundamental role in such problems. If time permits, I will choose a couple of simple and elegant proofs from the vast and varied literature to enjoy together. And I'm going to take a brief pause after each segment of the talk in case you would like some clarifications. Let's get started with some of the nomenclature in the title. The word patterns is an overused one in our vocabulary and in popular culture. We see them everywhere. They appear in old and new architectural marvels, in arts, crafts, and music, in knitting and sewing, and in fact, in most expressions of human creativity. There is even an English word called apophenia or patternicity, which means the human tendency to see patterns and shapes in random objects or situations. A very common example of this is cloud patterns, like this one, where you see a cloud shaped like a dinosaur. Such patterns don't necessarily mean anything, but they are pleasing to the eye, like this star shape on a clover leaf. Sometimes they unwittingly bring a smile to our faces, like this sink tap shaped like a funny face. But not all patterns are frivolous or figments of our imagination. Their occurrence sometimes signals the presence of phenomena that are important for diagnostic and predictive purposes. Perhaps an example of this could be the patterns that physicians look for in X-ray and MRI results. For example, this medical image by the American Cancer Society for breast cancer identification. It is a point of debate for scholars in human psychology whether a pattern already exists in nature or whether it has to be found. Here, for example, one can argue that the pattern of a pouncing tiger was invented to fit into the jigsaw puzzle and would be difficult to spot if the boundary lines were erased. Sometimes, as in this interplay of water and light, the tessellated pattern is clear for everyone to see. But even when a pattern is clear, it may not always be easy to identify what it represents. Take, for example, this collection of discs of various sizes. While the packing of circles is obvious, it is less clear what it actually is. In case you are wondering, it is in fact an aerial shot of a logjam floating down a river. We will primarily be concerned with the problem of identifying some structure embedded in a set of points that may not be obvious from a simple visualization of the set. An example could be this collection of blue, orange, and pink pixels, which on the left just looks like a disorganized bunch, but properly coalesced generate three identical rectangular columns of the same shape and size. Pattern recognition is a term that many applied scientists and engineers are familiar with in various fields of specialization, especially in machine learning and AI. This slide lists some of its real-world applications. Patterns have been used in disease recognition and in imaging for over a decade. In financial companies, pattern recognition systems help recognize data related to trends in financial markets. The fingerprint recognition technique is the dominant technology in the biometric market. Speech recognition is another hugely successful area where patterns are routinely identified to find meaningful words. The oil and gas industry uses pattern recognition in the analysis of minerals, energy sources, and their effect on various geographical terrains. Most of these applications rely on vast quantities of data and on algorithms to efficiently sort and classify this data into meaningful patterns. In contrast, the pure mathematical approach to pattern identification is still in its infancy. Since we only deal with theoretically provable results, the patterns that we can tackle are often simplistic, involving a few points, a geometric shape, or a functional relation. Nonetheless, within these limitations, it is a vibrant research area that lies at the interface of several subdisciplines of mathematics, like geometric measure theory, harmonic analysis, number theory, ergodic theory, and probability, and it boasts an extensive toolkit that draws from all of these areas. The overarching question in this field is simple to state. Knowing some rudimentary information about a set, such as its size or some mild structural properties, what can we infer about the patterns that lie within the set? Let us rephrase the question in the earlier slide in a bit more precise way. Does a small or a sparse set contain a prescribed configuration? Must every large set contain one? Stated in this level of generality, the questions lack precision. What do the words thin, sparse, large mean in this context? And what is a configuration? Let us try to unpack these words one by one. Small or large refer to the size of a set. How do we measure size? There are many ways. One could simply count the number of points in the set, in other words, use its cardinality. But of course, if the set is infinite, that's not terribly helpful. One could then appeal to measure theory using notions such as length, area, or volume, or more generally, Lebesgue measure in Euclidean spaces to quantify size. Measure is by no means the only metric of size. There are other notions such as dimension or density. We will give precise definitions of these terms as we progress through the talk. So much for size. What about configuration? In principle, a configuration could be any prescribed set. Such a set could be geometric, for example, specially arranged points on a line or on a curve, the vertices of a polygon. It could also be algebraic, such as the solution of a polynomial equation or of a system of such equations. Let's try a cartoon picture. Suppose the set under consideration is the collection of blue dots here. Based on inspection, the set does not appear to have any special characteristics. Let's bring a configuration into the picture. Suppose that the configuration is a three-point set. Say these three vertices of an isosceles triangle. One possible pattern question could be, does our blue set contain a congruent copy of this triangle? Equivalently stated, are there 3 points in this blue set that exactly match the triplet of red points, possibly up to translation and rotation? An alternative question could be to ask for a similar copy rather than a congruent copy. Here, we allow dilations in addition to translation and rotation. Let me stop briefly to see if there are any questions and clarifications about the formulation of the problem before we move on.
Hello everyone, Professor Malabika is with us. Anybody has a question can ask directly or in chat. So Malabika, Ajit Iqbal Singh has asked dilation or rotation. Or you allow both, is it?
So for a similar copy,
we allow translation, rotation, and dilation, whereas for a congruent copy, it is simply translation and rotation.
Okay. Ajit, does it's okay, right? Anybody else? Maybe we can go ahead. People can ask later also.
Here, for example, technique is the dominant technology in the. Must every large set contain one?
Okay, I'm sorry that somehow it reset. So I'll need some help, Malabika, in finding the right slide. Right now, am I too far?
This
No, I think you should be looking at talk part 2. So
this
I
is
can
part
see
1.
that you're still using part 1.
Okay, okay.
It's a different file.
Fine.
Hello? Yeah, shall I play Amber the second?
No, it will just start playing. I had to open the other file.
Okay, yeah.
So I'll just take a second to share it.
Sample of some fundamental and representative results on sets and configurations. A truly foundational result that has launched immense activity in many directions of mathematics is Zemuredi's theorem. Incidentally, this is also a result that makes use of a notion of size called density, mentioned earlier. Let's start with the definition. Let E be a subset of the positive integers. Given any large integer capital N, let us consider the proportion of the first n integers that are in E. The asymptotic density of E is by definition the limit superior of this proportion as capital N goes to infinity. Zemuredi's theorem states that any subset of integers with positive asymptotic density contains arbitrarily long arithmetic progressions. Let us recall that an arithmetic progression of length k is a set of k equally spaced points. Henri Zemuredi has made transformative contributions to many areas of mathematics, for which he was awarded the Abel Prize in 2012 by the Norwegian Academy of Sciences. In their press release, the Academy singled out this one theorem from Zemuredi's huge body of work. The announcement reads in part, quote, Zemuredi's proof was a masterpiece of combinatorial reasoning and was immediately recognized to be of exceptional depth and importance. A key step in the proof, now known as the Zemuredi regularity lemma, is a structural classification of large graphs. End quote. Zemuredi's theorem has many consequences. One way to interpret it is as a statement about sets and configurations. Why? Because having positive density is a quantification of the large size of the set. Arithmetic progression is an example of a pattern or a configuration. This large set E contains this pattern of a progression. What happens for sets of zero density? Here, the picture is more varied. On one hand, there are classical constructions of Salem and Spencer and also Behrend that demonstrate large subsets of the integers that are progression-free. On the other hand, there are other large subsets of integers that do contain long progressions. Examples of this are random sets, where the elements are chosen to belong to the set depending on a random mechanism, like flipping a coin. Another famous example of a zero density set in the integers with arbitrarily long arithmetic progressions is the set of primes, as shown by Green and Tau. Is there an analog of Zemuredi's theorem in the continuum? Let us start by formulating a prototypical question. Suppose you are given a class of subsets, script E, in n-dimensional real Euclidean space, whose members are large in some concrete sense. You are also allowed to choose a collection of geometric configurations, denoted script F. The question is, must every set capital E in script E contain at least one of the prescribed configurations capital F in script F? For example, take a fixed set capital F on the real line. Is there a geometrically similar copy of capital F in every set of positive Lebesgue measure? If you are not familiar with the term Lebesgue measure yet, as a rough approximation, just think of a set on the real line with non-zero length. In this question, script E is the collection of sets of positive Lebesgue measure, and script F is the collection of all affine copies of capital F. If the answer to this question is yes, let us agree to call capital F universal. It is a classical result in measure theory due to Steinhaus that all finite sets are universal. To break it down, what that means is, given any finite set capital F in R and any real set E of positive Lebesgue measure, there exists a translation parameter X and a non-zero dilation parameter T such that X plus TF is contained in E. The proof of Steinhaus's theorem is such a beautiful argument that I have never been able to resist sharing it. The proof outlined in this slide is in the special case where capital F is the 3-point set -1, 0, 1, so that the configuration space, script F, consists of 3-term arithmetic progressions. How can we show that every set E of positive Lebesgue measure contains a non-trivial 3-term arithmetic progression? A key tool is the Lebesgue density theorem, which says that almost every point X in E is a density point. Let's recall that a point X in E is a density point if the proportion of an interval centered at X occupied by E converges to 1 as the interval shrinks to its center X. This means that the measure of the set E intersected with the interval essentially fills out the entire interval in length and is therefore close to 2R for small r. Aiming for a contradiction, let us assume that capital E has no affine copy of this F. That means that for every positive T, either X minus T or X plus T is not in E. This in turn implies that at least half of the measure of the interval X minus R to X plus R is not in E, forcing the intersection of E with this interval to be less than or equal to half the length of the interval, which is R. And this, of course, contradicts Lebesgue density. A very similar proof, with minor modifications but no new ideas, also holds for any finite set, and I invite the students in the audience to give this argument a try in the more general context. The enticingly simple proof of Steinhaus's theorem leads to a natural question. What about infinite configurations F? Does there exist an infinite universal set? This stunningly simple question remains one of the notorious open problems in the field, called the Erdős similarity problem. Erdős stated in his Scottish Book of Problems that he hoped there was no such set. He also announced a $100 cash prize for it, which must be one of the world's hardest ways to win $100. This question, incidentally, was a follow-up to an earlier question, also by Erdős, involving only translations rather than affine copies. Given a sequence xn converging to 0, does every set E of positive Lebesgue measure contain a translate of the sequence xn? This question was answered in the negative by Borwin and Dieter in 1978. Erdős's conjecture states that every infinite set must be non-universal. In other words, there exists a set E of positive measure which does not contain any non-trivial affine copy of F. The conjecture has been verified for a number of infinite sets, such as slowly decaying sequences, and for certain infinite subsets, but remains open in full generality. In particular, it is not known whether the simplest geometric sequence 2 to the minus n is universal or not. Even after so many years, I find it amazing that such a natural question, stemming from such an easy proof such as Steinhaus's, should turn out to be so challenging. But it does suggest other avenues of approach. Maybe non-trivial Lebesgue measure is not the only quantification of size that we can exploit. Are there other sets of Lebesgue measure 0, but large in some other quantifiable way, which contains affine copies of all finite sets? This brings me to the notion of dimension. After all, in the plane, both a point and a line have Lebesgue measure 0, but they are certainly not of the same size. They have different dimensions. Now, there are several distinct definitions of dimension in the literature. Let me start with the simplest one, namely Minkowski or box counting dimension. Given a Borel set E in Rn, let us cover capital E as efficiently as possible using balls of radius epsilon. If such a cover involves roughly epsilon to the minus alpha many such balls, then we say that E has Minkowski dimension alpha. Hausdorff dimension is another notion of size. It also measures the spread of a set. The Hausdorff dimension of a Borel set E is the supremum value of alpha such that E supports a measure mu, a probability measure mu, obeying a ball condition of order alpha. Namely, mu assigns every ball a mass no larger than a constant multiple of the radius of the ball raised to the power alpha. It is well known that the Hausdorff dimension of any Borel set is dominated by its Minkowski dimension. This inequality can be strict. For example, the set of rationals has Hausdorff dimension 0, but Minkowski dimension 1. Why do we need all these definitions? Many reasons, the primary one being that they offer a finer calibration of size than the standard Lebesgue measure. Every set of positive Lebesgue measure in Rn has full dimension, whether Hausdorff or Minkowski. The converse is not true. There are many sets of Lebesgue measure 0 that have full dimension. As a sanity check, all these definitions of dimension agree with our existing geometric notion of dimension for curves, surfaces, and other algebraic sets. So no matter what notion of dimension you choose, a curve will always have dimension 1, a surface will have dimension 2, and so on. The real impact of these notions of dimension lies in their ability to assign a quantitative measure of size to objects that are less regular, such as fractals, where the notion of integer dimension is no longer meaningful. For example, the standard Cantor middle third set has Hausdorff dimension log 2 over log 3. Here's another example of a fractal, the Sierpinski triangle. You get it by a Cantor-like process by starting with an equilateral triangle and then progressively removing smaller equilateral subtriangles from it at every stage. The resulting fractal, I'll let you check, has both Hausdorff and Minkowski dimension log 3 to the base 2. The standard Brownian motion path in the plane has Hausdorff dimension 3/2. With these revised notions behind us, let us circle back to take another look at the question of universality. We already know that every set of positive Lebesgue measure contains an affine copy of every finite configuration. Is it possible that there is a Lebesgue null subset of full Hausdorff dimension that has the same property? Is it possible, being a little bit more ambitious, that every full dimensional Lebesgue null set has this property? Despite the lack of progress in the original similarity problem, there has been a tremendous amount of activity on these revised questions. The answer to the first question is yes. The answer to the second one is no. Andres Mathe has produced a compact set, not just of full dimension, but amazingly of dimension 0, that contains similar copies of all finite sets. On the flip side, Thomas Skeletti has constructed a full dimensional set on the real line that does not contain any non-trivial arithmetic progression, and in particular, not in more generally, his proof extends to any prefixed 3-point set. Such results have resulted in many generalizations, and I have mentioned some of the current researchers in the area. It would be remiss of me to not mention another of my favorite problems, namely the Kakeya problem, which among its many manifestations can also be thought of as a problem about sets and configurations. The original question by Japanese mathematician Soichi Kakeya asks, what is the least area of a convex set in the plane within which a needle of unit length can turn full circle? Paul showed that the answer is an equilateral triangle of unit height. If you remove the requirement of convexity, then the triangle is no longer the winner. The deltoid, for example, is a better candidate. But is it the smallest? The real surprise is that there is a planar set of Lebesgue measure 0 that contains the unit line segment in every direction. Such a construction was given by the Russian mathematician Besikovich around 1920. Such a set is now called a Kakeya-Besikovich set. The Kakeya-Besikovich set has far-reaching consequences in many areas of mathematics, but without getting into all the elegant theory that it has generated, one way to view it is as a set that contains many patterns. The patterns are the differently oriented line segments. The reason that Besikovich's construction is so counterintuitive is because how can a set with such an abundance of patterns be so sparse? That begs the question, how small can a Kakeya-Besikovich set really be? The famous Kakeya conjecture says that no such set can have less than full dimension. The conjecture has been proved only in dimension 2 and remains open in full generality in higher dimensions. I have listed the authors of some of the landmark results in the field that have resulted in incremental progress on the dimension bound over the years. Before we continue, let me pause briefly to see if there are any questions about the material so far.
Yeah, so
Part of my
can I ask a question? This Semerides theorem has now had an ergodic theoretic proof also, which was somewhat simpler.
Yes, that is correct. So there is an ergodic theoretic proof of Semerides theorem. Semerides himself gave a combinatorial proof, and then later on, Timothy Gowers gave a Fourier analytic proof of the same theorem. So there are at least three distinct proofs of Semerides theorem. The latest proof, the one due to Gowers, has launched a lot of activity. For example, some of the notions of size, such as Gowers norms, stems from that proof. And those have in turn been very influential in pattern problems. The ergodic theoretic proof is also been very impactful. For example, one of the strongest results to date on pattern questions due to Tamar Ziegler actually relies on the ergodic theoretic methods.
Okay. One more question. It's linked to coloring problem also, right?
That is correct.
It has quite a big impact on coloring problem, right?
Yes. So the original, there is the k equal to 3 version of Semerides theorem is known as Roth's theorem. And there is the coloring version of it, of Semerides theorem, goes by the name of van der Waals theorem. And, yes, these results have quite an impact on coloring problems as well.
Yeah, thank you. Any other questions from audience?
Yeah, Riddhi, here, Sophie.
Yeah.
Yeah, I mean, in the infinite dimensional context, such ideas could perhaps be pursued if you define the size in terms of prevalence. Do you have any idea about that?
I don't know what would a typical problem in the infinite dimensional context look like?
The search for an infinite dimensional space which contains copies of a given collection of objects of Banach spaces. Then the question is whether you can embed it in an isometric fashion, in a Lipschitz manner, or whatever. So there are some results, but then I have a hazy idea of space being prevalent, which can be used to embed objects from a given collection into a given into some nice object from that collection of objects.
I am not aware of the definition of prevalence, but I know that recently there has been some work in the infinite dimensional Banach space setting of certain pattern problems. The one that I am most familiar with is known as Falconer's distance problem. So it's a statement which says in the finite dimensional Euclidean setting, the statement is roughly says that if you have a set with large Hausdorff dimension and you look at the distance set, so the distance set is the set of all distances joining two distinct points within the set, that's a set on the non-negative real axis, then such a set must be of either full dimension or positive Lebesgue measure. Now, this is a finite dimensional statement and it is still an open problem. However, there has been extensions of this result in the infinite dimensional Banach space context. So as the talk is going on, I'm going to sort of look up the archive link and post it in the chat window so that you can take a look. And that's
that would be great.
One infinite dimensional rendition of a patterns problem that I'm aware of.
Great.
Okay.
Yeah, I'll look forward to that link. Thank you.
So there is one more question by a student. What is the definition of large set of zero density? Malvika, that's, I think you
Yes,
use this.
Deepika asked this. And Deepika, your question could not be better timed because right in this next part of my talk, I'm going to give you an example of a large set of zero density. So I said that I was going to talk about a proof or two. And the first proof that I'm going to talk about is a classical result by Berendt, who constructs a progression-free large set in the integers. And I'm going to show you this beautiful construction in a moment. It will have zero density, but you will also see in what sense it is large. So it's a subset of 1 through n, but its cardinality is larger than n to the power of 1 minus epsilon for every epsilon. It's large in that sense.
Okay, great. So let's start the next talk, next part of the talk. Can we start that?
Let me pick out two results that on one hand have been impactful in the literature on sets and configurations, and whose proofs at the same time are simple and elegant and can be enjoyed without any specialized knowledge. One is an old result due to Berendt on constructing a large progression-free subset of the integers between 1 and n. The other one is of more recent vintage due to Keleti about a full dimensional set in the reals that avoids all non-trivial solutions of the equation x1 plus x4 equals x2 plus x3. The trivial solutions are the ones where x1, x4 is some permutation of x2 and x3. So we place the restriction that x1 has to be strictly smaller than x2, which could be smaller than or equal to x3, and x3 has to be strictly smaller than x4 and have this equation hold. Let's start with Berendt's construction. Remember, we are trying to find a large subset of the integers from 0 to n, which is progression free. Let's pick capital N to be of the form d to the power of little n, where d and n are large integers. Any integer capital X between 0 and n minus 1 can be written in terms of its digit expansion with respect to the base d. In other words, capital X is a finite sum of the form xj d to the power of j, where each digit xj can only take integer values between 0 and d minus 1. For every integer capital R, positive, we construct a set called E sub nr, which consists of all integers capital X such that every digit is at most d over 3, and in addition, the vector of digits lies on a sphere of radius square root of r. The lovely observation of Solomon Spencer and then Behrend was that for any r, the set E sub nr is progression free. Why is that? Let's look at the defining equation of a progression, namely x plus y equals 2z. Then the restriction on the digits implies that the vector of digits little x, little y, and little z continue to obey the same relation as well. But by definition of E sub nr, the vector of digits x, y, and z lie on a sphere, and a sphere cannot contain 3 distinct collinear points. So at least 2, and hence all of these points must be identical. Next, we argue that at least one of these sets E sub nr must be large. This follows from pigeonholing. Since each xj is at most d, the total number of possible choices of r, which is absolute value of x squared, is at most n times d squared. On the other hand, the union of all the sets E sub nr covers all possible numbers with this property, with whose digits have this property, and therefore has cardinality at least d to the n over 3. Therefore, there must exist some r for which E sub nr has cardinality d to the power of n over 3 divided by little n d squared, and after converting everything back to capital N, this turns out to be the claimed size. This entire proof was predicated on this simple geometric observation that an integer was expressed as a vector of digits, and the vector was chosen to lie on a geometric object that could not contain 3 points on a line. Let's look at Keleti's construction next, where the goal is to create a large avoiding set for the equation x1 plus x4 equals x2 plus x3. The construction is very similar to the standard Cantor construction, but with a twist where we keep tabs on selected intervals to be used in posterity. Start with the unit interval 0 to 1 and decompose it into 12 equal pieces. Number them 0 to 11 and pick the intervals that are numbered 3 mod 6. In other words, the intervals marked 3 and the interval marked 9. At this stage, before proceeding any further, start up a queue of intervals that have been selected up to now. Right now, the queue has 3 members, which we call J1, J2, and J3. What is J1? J1 is the interval 0 to 1, which was the selected interval at the first stage. J2 is this interval right here. It was chosen, it was one of the intervals chosen at the second stage. And this is J3. It's the other interval chosen at the second stage. In general, at the end of step m-1, we have a certain number of selected intervals and a separate queue consisting of all the intervals that have been selected up until that stage. Of course, the number of elements in the queue far exceeds the number of basic intervals present at any stage. Why? Because not only does the queue contain all of these intervals, it contains all the intervals from previous steps as well. At the mth stage of the construction, we split each existing basic interval from the m-1th stage into 6m equal parts. But how we select the basic intervals now depends on j sub m-1, the m-1th member of the queue that we have going. If the parent interval at the m-1th stage is contained in j sub m-1, remember j sub m-1 could be one of these. So if this one is contained in j sub m-1, say, then we decompose it into 6m subintervals and pick the ones that are of the form 3 mod 6. So the ones marked 3, 9, 15, and so on. However, if the parent interval is disjoint from j sub m-1, so in this case, if j sub m-1 is this one, this one is disjoint from it, then once again, we split it into 6m pieces, but then pick the ones that are 0 mod 6, so 0, 6, 12, and so on. I call it a Cantor construction with memory because the procedure retains the information about selections made at all previous steps, and later selections are predicated on certain selected intervals chosen much earlier in the process. The final Cantor set capital E is the one obtained by intersecting the family of iterates E sub m, where E sub m is the union of selected basic intervals at step m. Why does such a set avoid non-trivial solutions of the interval x2 minus x1 equals x4 minus x3? Okay, so we argue by contradiction. If the difference x2 minus x1 is non-zero, then there is a step in the construction where x1 becomes separated from the others. In other words, x1 lies in some basic interval I that is distinct from the other three. This selected interval I joins the queue and becomes j sub m-1 for some m. At step m of the construction, j sub m-1 plays a decisive role. x1 lies in j sub m-1, so the m-1th level basic interval containing x1 is chosen using the rule 3 mod 6, whereas x2, x3, and x4, which were not in j-1, though their parent intervals go through a different selection mechanism, so their indices are of the form 0 mod 6. As a result, x2 minus x1 and x4 minus x3 are simply not of the same form and cannot match up, which yields the desired contradiction. Let me wind down by saying that the area of sets and patterns is a huge one, teeming with many different techniques ranging from incidence geometry to Fourier integral operators. By necessity in this talk, I kept to results that are easily statable and provable, but there is enormous variety in the literature, both in terms of knowns and unknowns, as well as in methods. Most importantly, there remain many patterns that lie beyond the scope of available techniques. And I hope that such questions will keep us busy for a long time to come. Thank you very much for your attention.
Thank you, Malvika. It's a wonderful talk, very clear and lucid. Do people have questions for this section, the last one?
Probably not specifically pertinent to the last one, but I had a general question.
Sure, go ahead, Gautam.
Malabika, hello, this is Gautam here.
Hi, Gautam. Good evening.
Yeah, good, whatever time of the day it is in your part of the world. Good morning, I suppose, right?
Yes.
So Malabika, it's quite likely there's something I might have missed. This is about the issue of congruence versus similarity. So I can sort of see the posing of the problem with congruence front and center, because in some sense this parallels this is sort of the continuum version of looking for arithmetic progressions, where you don't care where a particular arithmetic progression starts out. This seems like it models translations. But I was wondering, there's sort of two linked questions. If one also allows similarity, as opposed to just congruent configurations, I couldn't figure out, does this make the underlying problem easier or harder? That was one part of my question. And the other part was, about motivations. Is similarity motivated by this phenomenon of self-similarity that one sees in fractals that arise in the context of complex dynamics?
Okay, so let's try to take the two questions apart. So first of all, whether you are the similarity rather than congruence is often designed to make the problem non-trivial. So for example, let's look at the 3-point set, capital F, that we looked at, which is -1, 0, 1. If we simply look at a congruent copy of this 3-point set, then and ask, does every set of positive Lebesgue measure contain a congruent copy of -1, 0, 1? The answer is an immediate no, because any small, the diameter of that 3-point set is 2. So any set of positive Lebesgue measure whose diameter is strictly smaller than 2 would not contain a congruent copy of F. So that's an immediate elimination of a question. So the question becomes non-trivial if we allow similar copies or congruent copies. Similar copy or affine copy. An affine copy of the 3-point set, -1, 0, 1, becomes all possible 3-term arithmetic progressions. And that's a valid question, which does not depend on the location or on the spread of the set. Makes sense for any set of positive Lebesgue measure. So congruence is often too restrictive, affine makes the question meaningful. You asked whether it makes the question easier or harder. The answer depends on whether you are trying to prove or disprove the existence of a configuration. So, for example, in Erdős's question, he wanted to say that every set of positive, there is no set of positive, no infinite universal set, which meant that given any infinite set, he wanted to find some positive Lebesgue measure set which would avoid all affine copies of the given infinite set. That is a harder problem than finding a set of positive Lebesgue measure which avoids all translates or congruent copies of infinite patterns. So that easier question was resolved by Borwin and Detour, but the harder question of avoiding all affine copies actually remains open. On the other hand, if you look at it from the reverse direction, existence of patterns, then of course, existence of translates is a stronger criterion than the existence of an affine copy. So it depends on the formulation of the problem. In the context of Erdős's similarity question, the affine version is a stronger requirement than the congruent version. Does that answer the first part of your question?
Yes, yes, exactly. I somehow wasn't sure which is the harder problem. So I now understand. Thank you.
Right. So avoiding affine copies, that collection is a more abundant collection than all congruent copies. Therefore, avoiding a more abundant collection is a harder question.
Right. Yeah. Thanks.
The other part of your question was about whether the similarity has anything to do with the self-similarity of fractals. Well, yes and no. The patterns that one picks are certainly not dictated by any fractal per se. You choose the pattern that catches your fancy. And the sets that you construct or the sets that you look at are driven by application, or they have to be rigged in order to avoid certain configurations. So it may be the case, for example, that certain self-similar fractals are constructed in such a way that they offer preferential treatment to certain patterns. Just as an example, if you look at the Cantor middle third set, the way it is cooked up, it will always contain many, many three-term arithmetic progressions. It's in just the nature of the set. It may not contain that many four-term progressions, again, because of the construction. So whether we are looking at a similar copy of a pattern, not a congruent copy of a pattern, doesn't really rely on any fractal. The fractal or the set containing or avoiding the pattern follows once you have selected which pattern you are going after.
Yeah, but what I was trying to get at was in the kinds of problems that are formulated, how does one select the class? Typically, what is one looking for to formulate the structure of the class of configurations?
Meaning, how does one choose what kind of configuration to look for?
Well, I guess, a general question about problem formation. So all of the problems in this field, what dictates why the configurations are the way they are?
So I think this has a lot to do with the with the applications that people have in mind.
Uh-huh.
So, for example, if you are looking at it from a number theorist's point of view, um, all these questions by Zemeredi, by Green and Tao, Kohakawa, Lushak Rodel, and Ruja, I forgot to mention Ruja's contributions in this talk. A big part of their analysis is driven by this question: here is a certain equation, or here is a certain system of equations, and we want to look for whether such an equation admits non-trivial integer solutions or not.
Uh-huh.
So, recast in pattern language, this so-called pattern is a non-trivial solution of whichever equation the number theory people are interested in studying.
Uh-huh. I see.
So that's one application. Now, if you look at it, let's say, from a probabilist's or an ergodic theorist's point of view, then a probabilist may very well be interested in Brownian motion because it is such a fundamental object in so many fields, right?
Mm-hmm.
Then it becomes a natural question from a probabilist's point of view that if you let a Brownian motion path evolve and you track the progression of a set under a Brownian motion, if your original set was smooth or rough in some sense, then as you look at its Brownian image, how does this image change? That's a natural question from the probabilist's point of view, and it then gets recast as a pattern problem.
Right. Yeah.
So it's very much what the configuration is very
Mm-hmm.
much driven by the application that one has in mind.
Right. All right. Yeah. Thank you.
Anyone else has a question, comment? So if not, Malvika, let me ask you something. For real line, you took the set of finite points and affine map you applied to it to get into some set. So for higher dimension, you would take affine by linear transformations, right?
Yes.
And those questions are also being addressed? Or?
Yes. So there is a lot of work. So once you go to higher dimensions, even the plane, one can make certain choices. One can say which kind of transformations they will allow or
Okay.
exclude. For
Okay.
example, people can choose translation, dilation, and just leave it at that. Or they can choose to also introduce rotation or other linear transformations. So these questions, I talked about Keleti's example at the very end, and that was an example on the real line. It was a full dimensional set on the real line that avoids solutions of certain equations. There are many higher dimensional versions of that now. These, for example, a similar result is known in the plane that avoids vertices of a parallelogram. There are also many existence theorems, not avoidance theorems like Keleti's, but existence theorems where under certain largeness assumptions on the set, one is able to guarantee that certain geometric structures are guaranteed to lie in the set.
So in the higher dimension, it may be more interesting because in the real line, you only have these contractions and expansions, and most of the time you would contract to get somewhere. So
Yes,
yeah,
that is indeed correct.
okay.
Yeah, just a slight departure, Riddhi, I would like to ask if I'm allowed.
Yeah, sure. Go ahead.
Actually, I just would like to know, for example, if, in continuation of the theme that Professor Malabika has spoken about, if you have a closed curve, then, Tople's famous conjecture is that you can locate 4 points on its boundary which enclose a square. So you already have a pattern here, and this is the possible, configuration. For example, I mean, the existence of a square which lies on the boundary. Uh, you have an idea of the current state of art about this? Has it been resolved? I mean,
So I'm sorry, could you tell me again? I didn't catch what the question was. What's the conjecture?
On a closed curve, not necessarily convex. I mean, you can take it to be a smooth curve, let's say. Then howsoever complicated it is, you can locate 4 points on its boundary which encloses square.
Was it square or rectangle? I thought I
No,
saw
square,
one about
square.
rectangle.
Toplin's conjecture is square.
Okay.
So I'm not aware of this. Certainly, I don't know what the current state of the question is, but I know that many similar, like variants of this question have been addressed. I know that there was in a joint work with, I wasn't aware of this conjecture, so thank you for pointing that out to me. I will look this up, but I know that in joint work with a student, Robert Fraser, we looked at the question of arbitrary curves and subsets of them, and how and the locating progressions on the curve in terms of certain its parameters. So this is not exactly the question that you are asking. This is not the question of locating 4 corners of a square or of a rectangle, but it is a variant of the question about locating points on a curve which have certain geometric properties. And that we have indeed looked at.
Okay.
So you said it's called Toplitz's conjecture?
Exactly. Yeah. Terence Taub has done some breakthrough, but I'm unaware of that a few years back. I don't know the current state of art about this.
Okay, I'm going to look it up. Thank you so much for bringing it to my attention.
I saw something about a rectangle, and I'll send you a link when I find it.
Oh, I
a
see.
popular article.
So that is already settled, Riddhi?
Yeah, that's what I think. I don't remember too well, but I will send you a link when it was
Please
a
do.
popular
Please do,
article. Yeah.
Thank you.
So, are there any more technical questions or math question about the talk or anything else anybody wants to say?
Malabika, this is Sundari here. Riddhi.
Yeah, okay, sure.
Hi, Sundari.
Hi.
Is this Sundari from ISI?
Yes. Yes.
Oh, hi, long time no see.
Yeah.
Do you have, Sundari, you have any questions?
Yeah. So Malabika, you said, I mean, so you mentioned a proof or, I think it is Timothy Gower's proof where he uses the Fourier analysis and Fourier series techniques to prove something. Yes.
Yes.
So is there any other connection? I mean, I just want to understand, how is that it is connected to harmonic analysis or even Fourier analysis?
How is Zemmeredi's theorem associated to harmonic analysis or Fourier analysis?
I mean,
okay.
Pattern problem in general.
Sure. So that I think is not, I can explain. So let's say that you are trying to locate progressions in a set. Hello?
Yes.
You can still hear me, right? Okay. Yes. So suppose that you are trying to locate a 3-term arithmetic progression in a set. One way we could do this is by looking at a double integral. So let's say capital E is your set. If you look at the integral of the indicator function at x, the indicator function at y, and the integrator function at x plus y over 2, and if you integrate it over all possible x and y, and you show that this resulting quantity is strictly positive, in other words, non-zero, then you have established the existence of a 3-term arithmetic progression in the set E. Do we agree?
Okay, yes.
So because y, indicator of E at x is only 1 if x belongs to E. Similarly, Indicator at y is 1 only if y belongs to E, and indicator of x plus y over 2, that is 1 only if x plus y over 2 belongs to E. So for the product to be non-trivial, that is only possible if all three factors are non-zero, and therefore that is only possible if there is a three-term arithmetic progression in the set. So you look at this double integral, and this double integral, you can now you have transferred this pattern question into an analytical question. And now what one can do is you can recast these indicator functions in terms of their Fourier transform. If you are in the regime of integers, use the discrete Fourier transform in Z mod n. If you are in Euclidean space, use the traditional Euclidean Fourier transform. And then you bring to bear all the Fourier analytic machinery, and Tim Gowers actually brought in much heavier machinery than that to study the properties of this integral and show that under certain conditions, namely when E is of positive density, this integral expression is non-trivial.
Okay. Okay.
Yeah, I think one should look up these things, and it sounds very interesting.
Yes. Yes.
There is a much simpler version of Zemerides' theorem, which is not as substantial as Gowers' proof, which deals with all k, all progressions of all length. But there are simpler versions of this Fourier analytic proof for Roth's theorem when k equals 3. And I have found those as excellent for reading courses if you have an interested undergraduate or master's student.
Okay. Okay, that would be nice, Malabika. Can you just send the link? I mean, just put it in. I mean, if you have got something like that,
Yes,
you just
see
let
if
me
I
know
can
where
find
exactly I can.
the link to the Roth's theorem proof.
Yeah, that will be very nice.
So let's close the question answer session for technical questions. And thank you, Malvika. It has been wonderful. Can we ask you something about your mathematical journey as a student, how you chose mathematics, why you chose, whether you had support, anything you want to say?
So let's sort of break it up into small questions. So in terms of my mathematical journey, um, I think I don't think I was ever very good at mathematics as a student when I was in school, but I think I have always been impressed with the clarity and the beauty and the structure of mathematics and mathematical arguments. So even though I don't think that I showed any stunning aptitude for mathematics, it was clear to me that that's the best thing that I wanted to do, regardless of whether I could do it well or not. So at every stage of my journey, whenever I was faced with a decision as to whether I wanted to keep on trying to do more mathematics rather than take a different career option and try something else, I think the answer was always clear, even though I wasn't confident that I could succeed in what I was trying. It was very clear that I wanted to keep on trying because that was where I felt the happiest. I'm not sure if that answers your question, Riddhi. But I'll try to take questions and then and answer based on that.
Yeah. Okay, so maybe other people want to ask the questions about your mathematical journey, your life as a woman mathematician. Anybody? All right. I can continue asking if other people don't want to ask. There is something in chat. Fascinating talk, Malvika. People are very happy with your talk. So, could you say anything specific about being a woman mathematician? Whether it was, you think it was different, your mathematical career was different because you are a woman, or anything which affected your mathematics or your profession or your life in general?
Yes, of course. I mean, it is our who we are. Our identities are not really compartmentalized. I think our identities as women, as mothers, daughters, sisters, are sort and teachers, colleagues, these are all sort of intricately related with our identity as a mathematician. So I very much think that my mathematical journey has been shaped in really intricate ways, in complex ways, by my personal journey. So when I look back, there are certain decisions that shaped what I would or would not do. And this went into, for example, finding the right work life balance, how to decide whether to participate in a professional activity or to politely say no and set aside time for family instead. And conversely, to make a difficult decision to join a conference at a time when it was not clear to me whether would it be better to stay at home and attend to certain family matters instead. And there is never a right or a wrong answer to this. These are all deeply personal matters and requires in-depth thought, discussions with one's loved ones. And I think this also goes into many parts of our professional life. For example, the number of students that I have the capacity for, or how many students I can advise and to what extent. These are all dictated by certainly my identity as a woman and my existing commitments at any given stage of my career. So I think that sometimes people are able to set strict boundaries and say that this is what I will do and I will not do. And even though I do set certain boundaries for myself, I have found that often these boundaries are somewhat fluid. And I don't know whether this is a good thing or a bad thing. And I think maybe it's both. But to give a short answer, I think I'm giving a long answer to a short question, which is that yes, my gender identity is very deeply related with my professional identity.
Did you feel any hurdle as a young woman doing mathematics when you were younger, before, from
Oh,
family or from society? Or
Oh, absolutely, of course. So, one of the things that I constantly struggled with was a complete lack of confidence. I could never talk smart or look smart. I knew when I understood something and I knew when I was confused, but and I felt deeply uncomfortable when I was confused about something. And my strategy for when I was confused was to retract into myself and try to figure it out on my own. Whereas all around me, I saw my peers who were able to hold their own in a conversation, interact in real time, create arguments on the fly, and I was never such a fast thinker. So I never could really turn things around quickly. I deeply enjoyed them, but I never felt as if I belonged to that crowd. So I realized, I mean, of course, this realization came after an infinite amount of struggle and self-assessment and analysis. But I think at some point I realized that that's okay, that not all of us have to be painted with the same brush. As long as we all enjoy mathematics in some form, and we create that, give ourselves that space to enjoy mathematics on our own terms, ultimately that's what it matters. It is not about the image that we project. It's not about what we feel that others should think of us. It is about what we value, our own belief system of how we want to do math and enjoy math. Ultimately, that's all that it boils down to.
Thank you, Malvika. You answered my next question also, which was if you have any message for our younger women audience or any or math audience. Geeta
Geeta
wants.
has in the chat window, Geeta has,
Geeta wants to ask a question. That's what.
yes.
Geeta, go
So,
ahead.
Ridhya, you asked me to put the video on, and I am going to put it on, but I will tell you that once I put the video on, the audio sort of suffers.
Oh,
So
I see.
I will
Okay.
put it on. I don't know if you can see me, but
Malabika.
okay. If the audio gets choppy, I will close the video again.
Yeah.
So, Malabika, I wanted to ask you, in Canadian universities, what is the percentage of women in maths faculty in general? And are there any measures that are being taken to, I'm assuming that it's not very good. And are there any measures that are being taken to change this in any way?
So, as you can guess, it's a socially fraught issue. Now, at the undergraduate level, and to a certain extent at the graduate level, we still have a certain proportion of women. So at the undergraduate level, it is certainly bit somewhere around 40%, I would say, but then among the math faculty, as we progress up the ladder, the number drops off sharply. And in the STEM disciplines, is at the tenured or tenure track stage, I think the number it's different depending on the different subdisciplines of mathematics, but it's somewhere between 10% to 20%, which is not at all great. Now, are there measures that are being instituted? Yes. The government explicitly recognizes the need to promote not just women, but all underrepresented minorities. So now there is more of a federal initiative to recruit and to open up positions with an explicit mandate to target women and minority groups. So as to, for example, there are many sort of federally funded prestigious recognitions of excellence at the research level. One such position is called the Canada Research Chair. And it was found out that before any kind of awareness came along, a disproportionate number of these positions were held by men of a certain demographic, and there was hardly any representation of women and minority groups. And in fact, this was so lopsided that it actually went to court. I mean, so there was a legal battle, and the ones who brought the suit won, And as a result of which, now there is a concerted move to award these Canada Research Chairs to certain members of underrepresented groups to try to restore some kind of balance. There are explicit acknowledgements in most government websites that diversity is essential to excellence. There is this perception in not just in mathematics, in many science disciplines, that there is excellence and then there is diversity. And you can have one, but not the other. And by going for diversity, you are implicitly compromising on the excellence. And this could not be more wrong. And now I think there is a groundswell of awareness. We have a lot of ground to cover. Our numbers show that we have a lot of ground to cover, but at least there is an acknowledgement from the policymakers.
Thank you.
Before we go to next question, student Himanshu Lekharu has been asking this question. Can someone please suggest me some books from where I can read this?
Okay, so Himanshu, I don't know which particular things you mean. If you are trying to ask about patterns in fractals and their mathematical applications, then a wonderful book to at least get started on, this is by Kenneth Falconer. So I'll put the name of the author in the chat box. So hang on. So he has a couple of different books called mathematical, so fractals, their mathematical analysis and applications. You can start with those because these are easy to read. If you want some more advanced material in geometric measure theory, standard textbooks are by Pertti Mattila. He has many books. The one that I like very much is called Fourier Analysis and Hausdorff Dimension.
I think he may be interested in this density theory and these points.
Yeah.
How you?
So there is
he's reading ergodic theory currently. So
there is so if you are more in the discrete side of things and you want to read about those, this is an excellent book, Tao and Wu, Additive Combinatorics, especially for concerning Zemmeredi's theorem, different types of proofs of Zemmeredi's theorem, notions of density. That would be Tao and Wu's book.
Oh, that's wonderful. Himanshu, I suppose it answers your question. I guess so. So anyone else wants to ask Malabika a question? Now we see her, so it's, for me, it's more real when I see a person. Neela? Moa may have taught you. Neela.
So may I just want to thank Malvika for doing this because I know it's not easy to do this recording, and it was a beautiful recording. And she participated with us so early in the morning. So I want to sincerely thank on behalf of IWM and all of us. Yeah, that's it.
Thank you, Neela. No, it was a real pleasure. It was a pleasure. I wanted to make this work.
Moa?
No, it's fine.
Malabika, oh my God, and that's the familiar face. Hi.
Hi. So it's a very nice talk.
Thank you.
Hi, Mahua. Hi.
But somebody wanted to ask something, I heard.
How are you?
Yeah. I'm Padmati here.
Yeah. Go ahead, Padmati.
Malvika, hi. I'm Padmati here. I wanted to ask, how did you overcome the lack of confidence that you were having?
To be honest, Padmavati,
I don't think I have entirely overcome it. I struggle with lack of confidence often, but I think there is something that I have learned with which I use as ballast when I feel that I am incapable of completing something that I have undertaken. If I find myself feeling less capable, I think all of us do at some point in our lives, I think that there has been a realization that has come that helps me stay afloat. What I think I have realized over the years is I have learned to put more faith in myself, in knowing rather than trying to judge myself through the eyes of somebody else. Don't get me wrong. I deeply value, respect, and appreciate all the people who have supported me over the years. And this includes my family, this includes my teachers, my mentors, my friends, and others who have sometimes offered me advice. And I'm grateful for all of that. But at the end of the day, it is my journey and it is my life. And I need to make the decisions that are right for me. So when now I feel unsure, I am not confident if I can or cannot do something, the real question is for myself. Do I know what the next right thing is? Do I know what my next step ought to be? Not what somebody else tells me I should do. Do I know what I want to do? And if the answer to that question is yes, then that's victory for me. So the short answer to your question is, how did I overcome this lack of confidence? I cannot tell you that I am confident of what I do every single time, but I have learned to let go of other people's perception of me.
But you sure have a lot of clarity, and I'm very happy to see that. Did someone help you to achieve this kind of clarity or this way of thinking? Did you have a role model?
I have had many role models, and I should tell you that so there are. I'll start from my early childhood. Both my grandmother and my mother were teachers. My grandmother taught at a school, and my mother was a mathematics teacher in college. I met many people, many teachers, some of them were exemplary expositors over my academic journey. The clarity, I think, comes from a certain perception of our field. I have noticed that sometimes talks are given in a way, I don't know whether this is just the nature of our discipline or whether this is cultivated, but oftentimes talks are not very easy to grasp. And for me, in order to truly appreciate something, in order for me to say that, oh, I love this, this is beautiful, I have to first understand it. Otherwise, what am I approving? So I think one of the things that I have felt is to take responsibility for my presentations. That if I give a talk and if a truly interested undergraduate student or a first year graduate student cannot understand and appreciate that talk, then the onus is on me. It is not them, it is me. So I think that taking that responsibility, making myself accountable, has given me some amount of clarity in my exposition.
Thank you very much, Malvika. I really appreciate your patient given answers. Thank you very much.
That was really a
Very
beautiful
beautiful.
talk, very well done. And all the answers are so beautiful and so clearly put across that everybody is really happy, and I'm sure they will all be inspired by you.
Yeah.
And would anybody else want to ask a question, or one last question, or we close?
One last question, ma'am. Can I ask?
Somebody wants to ask.
Ma'am, so what kind of experiences you share? Do you have could be evolved or modified so that to address kind of issues that you face or many people face, like lack of confidence who come from the minority groups or from less privileged conditions? So if the system could be from top to bottom, like recently I have been a community of USA postdocs, and I was surprised that how much they were feeling depressed and very facing many mental problems, early career students. And I was very much surprised that such a condition in the US. And so and we are built up a community, means just a channel to discuss how something can be changed, but that discussion stops very early because we don't have any idea how this we can suggest something to take a common interest, because if sometimes
So,
one person or two-person could be strong enough like you to overcome those difficulty, but the common mass, like if there is 70 students there and 35 of them failing like the condition you were failed, so only one or two people would be strong enough to overcome that. How the system took care of the rest of them? If there is any suggestion or thought you have, or
Yeah.
people are thinking regarding that, top positions who are in
Yes.
the.
So, Devendra, that's a great question. Excellent question. Thank you. The issue of this feeling unsupported, having feeling depressed, and wondering uncertainty about the future, it is rampant in our community, especially among early career researchers. If I may make a suggestion, it is difficult to think that there has been any advantage, any upside to the pandemic. But if there is one positive that I can point to, that is that it has leveled the playing field. Look at us, all of us, the 40 some people here in this group, sitting in different corners of the planet, and we have come together on a common platform. So, something that I would suggest, there is tremendous strength in building community. And because of technology, internet, Zoom, meeting platforms, it is now much simpler to build a community. So, something that I would strongly suggest, if you have the time and the capacity to do it, is to put out a call for postdocs and graduate students in your research area across the world, certainly within India, and start up a meeting, a meeting like, let's say, once a month, maybe once a week, where you folks give like 5 or 10 minute lightning talks to present your research, to talk about job opportunities, to ask each other, how can I prepare? Do you want to look at my CV? Do you want to read my research statement and give me some feedback? There is enormous strength in building this network. And a big part of this loss of confidence comes from this this isolation, that I am alone and nobody really cares what I am up to. If you reach out to people at a similar career stage and start up a network, the conversations, the interactions, the dialogue, the professional and career development tools that you will have at your disposal will increase manyfold. I promise you that there will be some support that you will get, which is impossible to give you if you are sitting by yourself. So reach out to people, take an initiative, start up a community. It's an amazing experience.
We were doing like that actually. That
Really wonderful answer, Malavika. And we are all very thankful to you.
Here is, I mean, Sundari once again, and I'm sorry I blurted out something in between. But then, the last part which you have said, see, all through, I mean, I must say more than 20 years now that I was just away from mathematics. Okay. And really, basically, after my second daughter was born, so you know very well. So I would rather say after the pandemic, I'm really thankful for it. I mean, it happened only because of that. I was able to attend all these talks. Otherwise, I was never given a chance. Never. And nobody even bothered. Okay. Okay. I mean, so all the time, most of the time, I only came across people saying that, okay, she has already so much on her plate. So it doesn't matter. Okay. I want to see at least something that is there. Okay. So apart from this, I'm really thankful for that. And, you have mentioned it. And so I have a question. You're
Yes.
saying that, yeah, pardon me?
Go ahead.
Yeah. So I have a question. So when you're saying that, okay, you want to make so you said that you are going to really you always take the responsibility for your presentations. Okay. And so, so I always, everything, whatever, if I'm presenting something to my students or anybody, anywhere, always want to give them an intuition. And then it is not always so easy to understand it or to give something like that. So I really struggle. And most of the time I realize that the senior professor don't even bother. When I ask them, saying that, okay, I want to see where does this come from. I mean, nothing is going to come out of the blue. I will never be able to make a statement and say that, okay, this is going to be true. Let me try to prove it. That's not going to work. Is that correct? And so there should be something somewhere, right?
Yes.
So also I was just wondering, how was that possibly one can get something like that?
So if I understand correctly, you are asking how does one go about giving the intuition first in a way that people can easily grab onto?
Yes.
Okay. So part of it, I think it depends. So on one hand, I feel that for old results, classical results, things that have been around for a long time, and things that I may have read and thought about for a long, long period of time and discussed with many batches of students, of course, the more I explain to people, the better understanding I get. So it has been a joke of mine that I hand out, so I teach these courses, I give my students grades, but the person who benefits the most from this experience is the instructor.
Correct.
So every time I teach a course, I get a new insight into a result that I hadn't thought of before because somebody very truly intelligent pops a question and I realize, goodness gracious, I never thought of it this way. Now, for more recent advances, as research is evolving, newer and newer papers are coming up every single time. So, of course, with these new advances, I do not have yet the same depth of understanding, the insights. So, when I try to explain some of these new advances to the students in a seminar or in an advanced topics course, I start with the disclosure that what I am trying to reflect is my current understanding of the subject, and that it is intended to be a collaborative effort rather than me being a sage on a stage and lecturing to them. So I make it clear at the outset that the whole experience will be universally beneficial if everybody brings questions and everybody also pitches in to try to answer those questions. And I tell them right at the beginning that I am not going to have ready-made answers available to you the moment you pop it. But I promise you that if you give me a question that I don't know the answer to, I will go back, I will think about it, and I will come back with a better answer next time. And I am going to keep on improving on it until we run out of time. So it's this, I think, admission right at the beginning helps me and helps them also manage expectations. Because we are not, nobody's perfect.
Yeah, sure. Correct. I agree. I agree. I mean, most probably I expect too much of me. That's okay.
I have learned a lot of things, because we have our good days and bad days. So I will remember your talks, your advice, and your philosophy. And I'll go and look on YouTube because this talk is there. So it would really help many of us to revisit the talk. And whenever we feel down, we are going to look at it and get some points from that. Thank you very much, Malvika. And I think we close the session now. It was wonderful. Everybody is very happy. As I see, you can see the chat box, and students, seniors, everybody's like, I am really, really happy. And I'm so impressed. I don't know how to do this because I have like sometimes it's good, often it's bad. So the talks are really a problem, teaching is a problem, but I will remember that you said that one can learn. So it's still not too late to learn.
No. Thank you so much for having me. I have been aware of your organization and I speak to everybody about it whenever I run into someone. I've been aware of the fantastic work that IWM does. Thank you for thinking of me and giving me this opportunity. It was lovely meeting everybody, even if virtually.
That was nice. We are 14 people and everybody does their bit, and it's been good so far. And we look forward to more cooperation and collaboration with you in future.
The 3 cheers for Riddhi, for Neela, for Geeta, Sundari, and Malabika. Happy New Year.
Happy New Year.
Happy New Year. Bye.
Everyone.
Okay.
These are regular fixed point in our. I'm saying Ajit. For her, we have to say 3 cheers.
Yeah. Right. Yeah.
3 cheers. Hip hooray.
Thank you. Bye, everybody.
Bye.
See you.
Bye.
Bye. Bye, Malvika.
Bye. Thanks a lot, Malabika.
Yeah. She's gone. Bye.
Okay, I'll close the session.
Yeah, sure. Go ahead. Bye.
Bye-bye.